Thank you very much for being with us tonight. I'm Genevieve. This is Winston, Megan, Lauren, and Dina, and together we are Team Fluidics. We're very excited to tell you today about the categorization-based approach to the inspection process that we developed for Bowles Fluidic Corporation this semester. The Bowles Fluidic Corporation is located in Columbia, Maryland, and they are an engineering company that really specializes in creating these plastic, non-moving parts that are able to create oscillating movement. So you can see an example of the kind of parts they create in this video. So their parts have a variety of uses across different industries, but they're really focused in the automotive industry, and 75% of their revenue comes from the automotive industry. In fact, 85% of all cars in North America actually have a Bowles Fluidics windshield washer nozzle in them. So it's definitely really focused on that, and because they're in the automotive industry, quality is extremely important to them. Because of this, they have a lot of processes that allow them to have great quality when they arrive at the end customer, and we're going to talk a little bit about that. So the parts are, all components are injection molded in Columbia, Maryland, and then after that they do go through an inspection process before it's being shipped to their second facility in Fresnillo, Mexico. In Fresnillo, all the parts are assembled and then inspected again before actually being shipped to the customer. So because of this, they have extremely low rates of defects in actually being shipped to the customer. However, we can really benefit in being able to identify those defects a little bit earlier, which is why we're focusing really early in the supply chain in the component inspection and integrated quality area. So I'm going to talk to you a little bit about how the integrated quality area actually works. So the current process is that about 130 boxes go through the integrated quality area every day. Currently they use a single shot sampling method. So what happens is that they take one shot per container, inspect that. If it passes, they go straight to the loading dock for shipment to Fresnillo. On the other hand, if there is a defect, there are two possible things that can happen. So the parts go to the hold list, and in the hold list, the part can either be approved by a quality engineer, in which case it will get sent to Fresnillo if the defect is not serious enough to receive any kind of warning. But it could also receive a quality alert, in which case it gets marked for sorting in Fresnillo and gets sent to Fresnillo as well. In very rare cases, the part is quarantined in Columbia if the defect is serious enough. So where does this leave us in terms of our project? The opportunity is that although they do really great at getting their parts to the end customer with no defects, you want to be able to catch it earlier. And currently, the system with the single shot sampling method doesn't work as well as we'd like it to, with 66% of defects detected in Fresnillo not ever being detected in the IQA. So I'm going to hand it over to Winston, who's going to tell you a little bit more about how we plan to solve this issue.
Thanks, Jen. Okay, so we took a lot of data at POC, and what we found was even though they're using the same exact system, one shot, one sample for all their parts aren't all equal. Some parts have a slightly higher chance of having a defect. And so what we are suggesting to them is to have a categorization-based approach. And this way they can focus their resources on parts that may have a slightly higher rate of defect. And so what that means for us is that instead of one state, they will now have two different states, a relaxed state and a tight state. Now, the relaxed state will be for high-performing parts that often can go through without problem, and will accelerate them through the IQA using a skip lot sampling method that will save them a lot of time. The time is made up in the tight state for parts that may need a little extra effort, so we'll have an increased sampling state in those parts that will help enhance the detection there. Now, parts can't just stay relaxed or tightened over time. They might change, and so what we're suggesting to them is that they implement a quick switching system in between the two states. And so what that would mean is, if on the relaxed state, a high-performing part happens to get a quality alert, then you will move into the tight state for future parts. On the other hand, if you're on the tight state, historically maybe not performing well, but if you have 5 consecutive non-defective lots doing really well, you get the opportunity to move over into the relaxed state. And so we're going to walk you through our design for the relaxed state and the tight state right now, okay? So, for the relaxed state, our goal for this was to save them as much time as possible, because these are parts that are going to do really well. And so when the lot comes in, you inspect the first part, the first box within the lot, and assuming that it's good, it moves directly to the loading dock. And then all of the intermediary boxes will move to the loading dock as well without any inspection, because you would assume that since this part is high quality that they would be okay. You inspect the last box and assume that it's okay as well. The entire lot gets shipped to Fresnillo, Mexico, where the parts are assembled. Now, on the other hand, if the first or the last box has an issue, the entire lot gets a quality alert, and then it gets shipped to Fresnillo with the quality alert. And so that way, you are still potentially catching defects if they're, within this high-performing part. So I'll pass it off now to Meg to talk a little bit about our Titan state.
Thank you, Winston. So before we move into our Titan state, we have to determine how to determine an appropriate sample size. So it would be desirable for bowls to sample every single part or box, so then they can have a complete understanding of the level of quality within each box. However, this is impossible due to time constraints. So it's often common for companies to sample a portion of each box through something called acceptance sampling. Acceptance sampling mandates that 0 defects be detected throughout the entire sample, and it's a great way to address the balance between being thorough in your inspection as well as being time efficient. So acceptance on 0 sampling plans, or AOZ plans, are a common thing that companies employ to accept only a sample of the parts. So this speculative-based model that you'll see up here is based on the Defense Contract Management Agency, and this is the sampling plan that we use, suggested to BFC, to determine the exact number of parts that they need to sample. So based on an average of 500 parts per box and an accepted quality level, or AQL, of 0.065%, we determined that bowls would need to sample 200 parts in order to implement a statistically significant system. Now, with their current time constraints and personnel constraints, this is currently infeasible. So with this being said, we would like to suggest 2 different methods for our Titan state. The first option is to purchase and implement a Keyence one-shot 3D measuring microscope. And this microscope would perform autonomous part inspection using a non-contact optical lens to measure these precise measurements that quality engineers normally find themselves doing in the IQA. This microscope takes around 30 to 45 seconds to inspect each part, which is a significant decrease in time relative to their status quo, which is around 15 to 30 minutes per part. So while bowls would incur a significant increase in sampling capacity with the implementation of this machine, it does come with its added high overhead cost of around $90,000, as well as additional training required for BFC employees to be integrated with this new technology. And with that being said, I'd like to pass it off to Lauren to discuss our other Titan state option.
Thank you, Megan. So on the other hand, we can implement a more cost-effective solution while still reducing the number of missed defects in the IQA. So option B for the Titan state is to implement a double sampling scheme similar to this here. We'll see that parts continue to inspection in the IQA as usual and will be inspected for their first time. Assuming that both of these boxes here pass their first inspection, they will then be sampled a second time. Now, in the case that a box fails either its first or second inspection, it will receive a quality alert and be sent to Fresnillo for sorting. Boxes that pass this double sampling scheme will also be sent to Fresnillo for final assembly. So the question becomes, how do we validate all of these inspection methods? And in order to do this, we designed a Monte Carlo simulation and developed an operating characteristics curve as shown here. You can see our current state in black, our relaxed state in blue, and our Titan double sampling scheme here in orange. We've graphed the probability of accepting a defect versus the probability of a defect occurring. So with our current system in place at BFC, represented in black, we can see that the relaxed state in the skip lot sampling method appears to perform slightly worse. However, as mentioned by Winston, this is only reserved for part numbers that have historically high performance characteristics, and therefore we reduce the probability of a faulty acceptance in this particular system. So moving over to the Titan state, the operating characteristic curve shows us that by implementing the system, we can reduce the probability of accepting defective parts. However, another important consideration is that BFC parts have low probability of defects, and therefore are only accounted in the left half of this plot. So while this is still an influential system, but not as influential as perhaps a Squiglia-based model, we believe that it is still a realistic and appropriate method to be using given our current time and resource constraints in the IQA. I will now pass it over to Gina to discuss our implementation plan.
All right, so in order to implement our system of the Titan relaxed state, we need to categorize the parts. So all new parts will be placed on the Titan state since we will have no information about their historical performance. However, if we put all of the parts that they currently have on the Titan state, we believe that the IQA will be overwhelmed with the time needed for the additional inspection. So we are suggesting a transition state. Each of their current parts will be placed in this transition state that uses their current sampling method of one-shot sampling. Once it goes through the transition state, it will then be categorized as relaxed state or the tightened state. So if it passes inspection, it will move on to the relaxed state, and if it fails, it will go to the tightened state. With our system, Bulls will not be required to spend money on items that are placed on the hold list for further review, leading to a potential savings of up to $53,000 per year. This doesn't even include the added benefit of saving shipping costs because they won't be sending as many bad parts to Fresnillo because they'll be caught earlier. They will also benefit because by catching defects earlier, they will be able to ensure more timely delivery to their customers. We've considered a lot of options for the IQA, and we believe that our system will allow BFC to more effectively inspect their parts and catch more defects using this categorization-based approach to sampling. We believe our system is practical, it's compatible with their current system, it's feasible, and it is cost-effective. And with that, we'd like to thank everyone who's helped us this semester, especially our project champion, Chicharina and Lisa Fernandez-Moya of Bulls Fluidics Corporation, and our project faculty advisor, Dr. Armstrong, and the rest of the class community. Thank you very much for coming today, and we would love to answer your questions.
All right, Bergen.
So in the data chart you talked about how the relaxed sampling scheme and the double sampling scheme compare to their current state. But did you consider how the machine would compare to that state?
That's a great question. Thank you for your question. So Bergen asked us how, we're showing you the tightened state, the relaxed state, but how does the machine compare to these things, right? And so honestly, the machine, let's see if we have this slide. Sorry. This here. Okay, so with the machine, you would increase your sampling rate a lot. Okay, and so if you had like a squiglia-based plan of a sampling rate of about 200, you can see it's plotted in black. Your operating characteristic curve dramatically shifts downstream, so you have a much, much stronger ability to detect if there's an error. Obviously, there's a huge trade-off, right? So it takes a lot more time to do that. And also, and there's a lot of costs associated with that. So you can kind of see how this, there's a trade-off between having a really high end at 200 and what we're suggesting that's more moderate around equals 2. Regardless, any of these systems, by increasing sample size, will be improving on the current state. So I hope that answered your question. Anybody else? Yeah.
Talk about if it passes 5 consecutive times in the tightened state, it would be moved to the relaxed state. Where does that come from?
So the question is, in our slide we talked about if there are 5 consecutive non-effective lots, why do we choose 5?
Thank you very much for your question. So this is something we talked extensively with BFC. So right now, an industry standard for this kind of a system is around 7, which, if you have 7 consecutive lots, your probability that you can trust those to be all good and move them over is pretty high. Right now, Bulls Fluidics Corporation, down in Fresnillo, when they're bringing in parts that they order, they use an N of 3. So we average that a good number would be 5 in order to do this. The probability of getting 5 consecutive lots is still a low probability, and therefore ensuring that we feel comfortable enough switching these parts over to this reduced sampling inspection method. Thanks.
Anybody else have a question?